Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
G'day everyone. So today we're continuing with estimation. Last time we talked about the method of moments, which is one that, and to recap, you would remember that in chapter 8 we were doing a bit of informal work as to how do you get confidence intervals. The best method was a physical quantity, but we did a few examples of that. But in chapter 9 we're focusing more on the properties of point estimates. And we already did the method of moments, which I guess that method is fairly systematic, but sometimes it might work and sometimes it might not work. And you remember you just write out all the theoretical moments, first moment, second moment, third moment, and so on, until, and then you write out what they're observed to be, the sample moments, and then you keep writing down equations until you get to a point where you can solve those for the unknown parameters. And you might have to write out more equations than you expect, or in some cases the moments might not exist or might not solve properly. But to the extent that that works, it gives you some estimators, and that's the method of moments. And the key property I said at the end of last time is that the method of moments estimators are consistent. So in a very large sample, they'll be near the true property. And actually, let me just say a little bit more about consistency. It's sort of a related fact, or it's even a theorem, you can find it as a theorem in the notes, is that remember we were talking about convergence in probability. If one random variable converges in probability to, so I just put brackets P for convergence in probability to a constant, it actually needed to be a constant, and probability goes to B, then you have x plus y, x minus y, x, y, x divided by y with a little asterisk, and then g of x. So all those converge to the things that you expect in probability to a plus b, a minus b, a, b. This would have to be a over b, so long as b non-zero, otherwise you couldn't make a conclusion. And this goes to g of a, and that's so long as g would have to be a continuous function at the point A. Okay, so that's kind of easy to prove from the definition. We don't want to go through epsilons and deltas, so we won't. And another theorem related to similar things is that if you have a random variable x that has a certain distribution, let me put it this way. I'll just say mu. I don't mean a mean. No, maybe mu is not the right letter for this. Greek letter nu, but this is any distribution, okay, and y converges in probability to 1. We've seen this sometimes, like the ratio of sample variance to true variance converges to 1. Then x over y converges in distribution to the same distribution. In other words, if you're dividing by something that tends to 1, then the ratio tends to the same distribution. We've actually used that a couple of times, maybe implicitly. Applications that, a t distribution with df degrees of freedom. Remember, that's the same as a square root of chi squared df divided by the number of degrees of freedom. It's z divided by that. Now, the chi squared, easy to check for very large, we know that chi squared with very large degrees of freedom is approximately df. So this thing that is on the denominator here, it's easy to prove that that converges in probability. It converges in probability to 1, because chi squared df has an expected value of df and variance df, 2 times df. So the ratio chi squared df over df tends to 1 in probability, and therefore it follows that this converges to normal 0, 1 as df tends to infinity. So all of that is as you have a very large number of degrees of freedom. And relatedly to that, if you have it's kind of the same result, but we talked about how when you're doing a different, let's just say the mean x bar minus mu divided by s over root n, we know that that is equal to x bar minus mu divided by sigma over root n, and then divided by s over sigma. Now we know that s converges in probability to sigma. Well, s squared converges in probability to sigma squared, s converges in probability to sigma, and s over sigma converges in probability to 1. So you're dividing, much like in the setup of this theorem, you're dividing by something that tends to 1. And so once again, this has the distribution that tends to normal 0, 1 in the same context. And so that was a couple of examples. We also talked about it in the context of f. So if you have, f with a and b degrees of freedom, which is, of course, as a reminder, that's chi squared a divided by a divided by chi squared b divided by b. This is kind of an informal notation. When I do this, I mean that the numerator and denominator are independent. So in case anyone was wondering about that, I'll just mention that the t and the f definitions are more specifically for the case where you have independent things on top and bottom. It's not t or f, if that's the case. Anyway, so that's what f is. And we know that the same argument as before, chi squared b divided by b, that's a thing that has converges to 1 in probability as b tends to infinity. Okay, so this FAB distribution, the distribution of that. So I should say that this convergence was in distribution. Okay? And then this also converges in distribution, no longer to normal 0, 1, just to the numerator. So chi squared a divided by a. Okay. So those were 3 applications of this second theorem. I guess the first theorem we also essentially, I'm not going to go into details. This is why method of moment estimators, if they exist, so if you can actually come up with a method of moment estimator, they are, the word I used was consistent. So, essentially, the sample moments are consistent for the true moments, law of large numbers, and therefore when you solve the sample moments for the true moments, you're using operations like this, and therefore it follows the sample estimators, the estimators that you get from the sample moments converge to the true values you get from the truth runners. That's one thing for consistency. Okay, let's now go on to talking about the method of maximum likelihood. So, the second method for obtaining point estimator. This is a systematic method. And I'd say that, in some sense it's a bit better than method of moments, in as much as you can say better. It's more general, but you can apply this to more situations. For instance, if the moments don't exist, you can still apply it. You can also apply it to non-IAD samples. That sometimes happens. You can just put together any pieces of information into a likelihood, and that likelihood function will let you do it. So let's do the method of maximum likelihood. This is always called MLE. Okay. So first of all, before we maximize the likelihood, we have to say what the likelihood function is. I'm going to do it in this notation X. I'm not going to specifically say it's an IID sample because that's a special case that we'll do most of the time, but it can be more general. So be a sample or other set of observations. It's quite general. Other set of observations related to an unknown, well, let's say it this way, a distribution with unknown parameter. Now you could have more than one, or parameters. Okay, theta. So I'll just put a little underline on theta. That's, in case there are two parameters, you just consider that a vector with two coordinates. But normally often there'll only be one or maybe two parameters. Okay, the likelihood of theta given an observation x. So I'm using lowercase for the observation because capital X is random and then lowercase x is the actual numbers, just a specific observation that it could be, is the function. Okay, now we're going to use a capital L for this function, L of theta, and then I'll also put x in the function. But as you'll see, x is not really the parameter of the function. X is just information that's given to you. The real thing that's the parameter of the function is theta, and we will be maximizing that function for theta. You find the theta that maximizes that function. So you should think of it as a function of theta, and x is just what's given. So it's kind of thinking backwards. Equals nothing other than the, I'll say f theta of x. So where f theta is the density function. So there's actually two cases. The continuous case you have density, and the discrete case you have a probability mass function. So density function, continuous case. But I'm going to call it f in both cases because I want to cover the same material. Probability mass function. In the discrete case of the observation x. And how does the theta come into it? Well, there's a different probability mass function for different parameters. So when the parameter is theta. So this is a long way of saying something that seems quite simple, but the key thing is it's now a function of theta. Normally you think of the mass function, the parameters are just information that sets up the function, and then you let the mass function or the density function vary across different x's. Now we're just changing what varies. The observation is what you've seen. It's an estimation. So you've seen a particular observation lowercase x. We're not letting that observation change. We're now thinking about how does the likelihood vary for the different parameters you could have chosen. And while so it's the same values, as the PDF or PMF, depending on whether it's continuous or discrete. But the input, every function has an input. You consider the likelihood function as a function whose input is the parameter theta, not the observation. Okay, while you might say, oh, so it's just a probability mass function, or it's just a probability density function. Considered as a function of theta, it is not a probability mass function or density function. As a function of theta, and by the way, it's almost always the case that theta is continuous. Even if it's a discrete count like binomial, still the parameter p that you're estimating is continuous. So it's almost always that theta is continuous. As a function of theta, L does not integrate to 1. Because, of course, it's not a probability mass function or density function of theta. It's only a probability density function of x. So, but we take x fixed, we consider it a function of theta. The maximum likelihood estimate, as you would expect, or estimates of theta given the observation x is the value theta hat. So I put the hat up, but we still use hat usually. Theta, which maximizes this function. So it becomes a maximization problem. So I write theta and x because, of course, you have to know the inputs, but I'm letting theta vary. I'm not letting x vary. X is just what I observed. Now, in rare cases, there might be multiple ones, multiple maximum or something like that. But most of the time, it's just a single maximum. In fact, most of the time, you can find that this likelihood is actually pretty much, or at least the log likelihood, which is just the log of L, usually that's often a concave function, like it's so a concave function always has a unique maximum. But we'll talk more about that later. That's not always the case, but it's very frequently the case. Okay, so let's now, I think that's enough examples, enough definition. Let's just do a very simple example. Now I could do it x1 up to xn, and then each of them is 0 or 1 according to whether it's a yes or a no. But I'm not going to do that. The number of people, and for the moment I'm going to have fixed sample sizes in a sample of size n from the population who have a certain property, could be a disease, who have disease D. Now, I'm being a bit vague about sample. Normally when you say a sample from a human population, you mean actually a simple random sample. And as you recall, a simple random sample generally means you actually have to have n different people, which means it's without replacement. So simple random samples are not quite as simple to... You can, unlike for the method of moments technically only works for IID. It doesn't have a setup for non-IID samples, although you could try it. This one works for any type of observation, IID, not IID, you can generalize it. But to actually write down the likelihood function for a sample without replacement becomes harder because each depends on the last. So instead of a simple random sample, I'm going to say it's an IID sample, which is the one that we're most used to, who have disease D. So it's an IID sample of size n from the population, and then the number of people who have disease D. So n has what distribution? Can anyone tell me? This is now sample with replacements. The general family is... I sample a fixed number, so n could be 100. So I sample 100 people and I ask how many have disease D, and what is the distribution? Binomial. Okay, so clearly n is fixed here, and then there is an unknown parameter p, and p is, can someone describe to me? What is the value of p? It's unknown. It's a proportion, right? You can always think of a binomial having a certain proportion or a certain probability of disease D in the population. Or well, more precisely, of people having disease D in the population. So that's what P is. Now we want to do an estimator of P. Let's before we actually do a maximum likelihood, let's compare the method of moments, because you can do method of moments here. The key is that xi is the indicator of the event that person I has the disease D. Okay, so that has a distribution that is Bernoulli P, right? So this is it does fit into the method of moments case, and we'll see in this case you actually get the same answer from the method of moments. And then x bar is equal to the number of people with disease, it's the number of people with disease, which is n, divided by the total number sampled, which is m. And that is often called, and then we set, so to do, that's x bar, and then the expected value of xi. To do the method of moments, you set that observed x bar to be the expected moment, which is p. Okay, and so p hat under the method of moments equals x bar, which is equal to n over n. Okay, so method of moments does work in this case. So let's check that the method of, this is just a baby example, we check that the maximum likelihood on the same observations. Maximum likelihood estimator. So the way you get it is quite different. It will end up being the same sample. So the likelihood function, okay, so we always write it with a capital L. I'll use lowercase l in a moment for log likelihood. Capital L, it's a likelihood of P given the, I'll write X. Now it turns out, X means the observations of all these things, does person I have disease D, is equal to, no, actually, I'm not, sorry. It turns out, it doesn't matter which person had disease D or not. We're just going to focus on the observation, capital N. Look, if you don't mind, I can just see there's going to be confusion in this from the fact that capital N and little n are not referring to the same thing. A little n was the size of it. So I'm going to leave little n as the sample size, and then we had a number of diseased people. So forgive me, but I'm going to change that to an m throughout. So m is the number of people with disease. That has a binomial distribution. X bar equals m over n. And then I can use little m. Okay, so little m is now going to be the observed value of capital M. Capital M is the number of diseased people, and then it's a function. Remember, the likelihood function treats the observation as a constant. It only treats the parameter as a variable. So the likelihood is nothing other than the density function, m of m, considered as a function of p. There is as a function of p. So it's just, we write down the density. Sorry, this is not it's actually a mass. I'll use p because it's actually the mass function. M is discrete, so it has a mass function. Considered as a function of p, that gives the likelihood. So we have to write down our standard n choose m, that's our binomial coefficient, p to the power m, 1 minus p to the power n minus p. Okay. So we'll find a quicker way to do this later, but for the moment, remember that p is the only thing that is varying. So now it's very tempting to, okay, just so that we've done it at least once, I am going to differentiate this because L prime of p, so by the way, to maximize the function of a continuous variable, this is continuous in p, so then the natural step is to try differentiating, and you know that the maximum must occur at a zero of the derivative, or maybe somewhere where the derivative doesn't exist. But here the derivative will always exist, and L prime is a function of P. Okay, so this will become a bit more complicated. So n choose m, P m to the power P minus 1. And then, so it's going to have to be a product rule, that guy times derivative of P to the m times this one undifferentiated, n minus m, plus, in this second case, I'm still going to have the n choose m, P to the m will remain undifferentiated, and then 1 minus P to the power n minus m must be differentiated. That gets a factor of n minus m, 1 minus P to the power n minus m minus 1. And in fact, because I was differentiating 1 minus P instead of P, the chain rule says that I'll have a minus 1 factor. So let's simplify that. N choose m is the common factor. I do get an m to the power. Let's just put. Yeah, something went wrong here. That was very bad. Okay, so this is actually m p to the m minus 1. At least ground. Yeah. So you either differentiate that and keep that constant, or you differentiate that and keep that constant. You add those two terms together and you get this. So yes, there is a m. I'm actually going to write it like this: m over p plus n minus m to the minus 1, m minus n divided by 1 minus p. And then there was a factor outside of that, which I haven't yet written, m p to the power n, 1 minus p to the power n minus n minus. Okay, so that's a fairly complicated thing, but this is going to be equal to 0. It's clearly that factor can never be 0. Those factors can never be 0. The only case where it can be 0 is only if, and you know that there must be, well, I guess we should probably check that there must be a maximum, but we will check that. It is equal to 0 only if m over p plus m minus n over 1 minus p equals 0, i.e., let's solve that for p. That will say that p over 1 minus p equals m divided by n minus n. If you solve that. Now, that still looks a little bit hard to solve for p, but of course you can do it with a linear behavior. A clever way to do it is to notice that p over 1 minus p, that's actually equal to 1 over 1 minus p minus 1. If you subtract the 1, you add the p. That would be it. If you don't like this method of doing it, then you can cross multiply and do it that way. But so it follows that 1 over 1 minus p, if I add 1 to both sides, is equal to m over n minus m plus 1 is equal to n over n minus m. So 1 minus p is equal to n minus m over n, is 1 minus m over n. So p, and this will be the, I'll put the hat on once I finally bother to solve it. This is the maximum likelihood estimator of p is m over n. Okay. Now, if you remember, that's actually exactly the same as what we did in the method of moments case. P hat equals m over n. So there shouldn't be any surprise that the best estimator of the true proportion is the sample proportion. But I just wanted to show you that you can deduce that in both cases. Now, check. Sometimes people are sloppy about this, but I want to at least once do it correctly. This is actually, you'll remember from your calculus class, you can't just set the derivative to 0 because some functions don't even have a maximum, or it might not be a global maximum even if it's a local maximum. So check that this is actually a maximum of L. Then, it's enough to observe L prime of P is, what if I make P smaller, right? At P equals m over n, we know that this factor is exactly 0. If P is smaller, it should be increasing. Well, that's right, because P smaller makes this positive term bigger and the negative term smaller. And if p larger, then the positive term gets smaller and the negative term gets bigger. So greater than 0 for p less than m over n, and L prime is less than 0 for p greater than m over n. Okay. Thus, p hat equals m over n is a global, if you're thinking back to your calculus course, max, or gives a global max of L. Okay? So that little sidebar is how you check that it actually is the maximum. Sometimes people are in a hurry to do it. Of course, it's most important just to find the value, but it's good to be sure that this actually works in a mathematical sense. So you get the same estimator both ways. Now, that was a little bit laborious, you'd probably agree with me, so I want to give you a way to do it that is slightly less laborious, and that's to use this log likelihood. Okay. Now, everything that I'm giving you as a method, slightly less laborious, every method I'm giving you is adapted to parameters that are continuous. So even for a binomial, the parameter p is continuous. If you can apply the method to parameters that only take whole number values or discrete parameters, but differentiating is not going to be the way to do it usually, because to find the maximum of a function of integers, there are other methods. Like you might set the derivative to 0 and get something that's not an integer. So you can apply the method in general, but not just by differentiating. You need to do a little bit more. So having said that, we're not emphasizing it. So, but you could do it if, for example, you regarded the proportion as known, but the actual number, you could have a binomial np where p is known and n is unknown. But to find the maximum likelihood value of n, you have to bear in mind it has to be a whole number. So we won't do that yet. But slightly less laborious is the log likelihood function. Now, there's nothing sophisticated here because the log likelihood function, little l of theta given the observation x is equal to the log of capital L of theta given x. Maybe often people assume that that's log base 10 or anything, but we're grown up now, so no one has any use for log base 10. So in case you like natural log, I use the word log for natural log only, because if you ever see me write log, I mean natural log, because that's the one that has the derivative that is 1 over x, which is the main property that we'll use. And so the natural log, and then quite obviously because it's an increasing function, maximizing L of theta, it happens if and only if you maximize little l of theta. Okay. To save writing, it is common, and possibly thinking as well, it is common to omit constants constant factors. So a constant factor is something like this n choose m here. In the context we were doing it, little n was not considered a parameter, it was just fixed. A parameter is something that can vary. So in that case, this was a constant. And you saw that it didn't play any role in finding the maximum. It would just, and I guess I should say, I sort of feel compelled to write positive constant factors. But of course, why would you have a negative constant factor? Because a likelihood function, by definition, is either a mass function or a density function. So the values are positive. So you shouldn't have any negative constants. But it's okay to omit positive constant factors from L, and that won't affect your ability to find the maximum. You know, because we don't actually care about the value of L at the maximum. We only care about where the maximum is. So, or which is the same as omitting any constant term, whether positive or negative. Once you take log of a positive number, you get any positive or negative constant term. Which, remember, factor is a multiplier. A term is a summand. Term from L of theta. Just to be totally clear, I mean an additive term, not a factor. Additive constant term from L of theta. Okay, so using this labor-saving device, okay, let's just do the last example using this labour-saving device, e.g. again. Okay, so just to recap, n is, little n is the sample size, which doesn't change. M is binomial np, and the likelihood is, as before, p given m is n choose m, p to the m, 1 minus p to the n minus m. Now, talking about this slightly less laborious, we'll just avoid that constant factor. It's not going to affect our calculation. And L of P. Now, you might say this is a bit of an abuse of notation if I can write down L with two different values that differ by a constant. This, for the purpose of maximising, it won't make a difference. I guess if you have any other purpose, you might want to be more careful. For maximising, it won't make any difference. So, so I'll just say omit the constant term. Okay, just in red. The constant term that would come from n choose m. Remember, when you take log of a product, you get a sum of the logs. That makes taking the maximum much easier. That's why you do log likelihood. So product here becomes p to the m, log of p to the m. The exponent comes out the front. So m natural log of p plus n minus m natural log of 1 minus p. Now, if I take the derivative of that, remember it's the derivative with respect to the unknown parameter, I get m over p. Natural log has derivative 1 over x, plus n minus m, but then when I'm doing 1 over 1 minus p, I get a minus out the front because of a chain rule. Chain rule always gives you minus out the front when you're differentiating that 1 minus p. So, and that is equal to 0 when p, okay, you can solve it the same way as before. P equals m over n. Okay. And that's what we call p hat. And if you had to specify, you would put MLE to say it's the maximum likelihood. And then, just to reassure you that it's the same consideration as to whether here's p hat, and you would find that it has a zero derivative there, it has a positive derivative here, and a negative derivative there. So clearly p hat is where the maximum of that likelihood function occurs. So that's maximum likelihood. Now I want to do some more. Basically, we've done the simple example twice. So let's do some more complicated examples. Of course, this is also one that we've done many times using method of moments. Up to x n our IID normal mu sigma squared. Okay. And now we consider mu and sigma squared both unknown, as is frequently the case. The likelihood function of, now I'll write it, you might be wondering why I put a semicolon. Do you remember I keep putting a semicolon? I treat everything after the semicolon as something that is just given, but not really a parameter, and nothing that I'm going to differentiate with respect to. So now, because there are two parameters, L is now a function of two input variables, but there's also some given information. Now, I encourage you to follow me and just put a little underline under x if you want to not have to write x1, x2, dot, whenever you're doing this. So it just saves it. So that means a vector of all the x inputs. And the likelihood is, of course, that the, well, it's nothing other than the px of x. I used f when I should use p, and then I used the p when I should use f. So this is a joint density. Okay? And luckily, it's easy to do joint densities when they're independent. We actually know how to do it in some non-independent cases, but joint density in the independent case is easy. The product I equals 1 to n of, you might remember, e to the minus a half. It would be, of course, e to the minus a half z squared. Z in the context of a normal mu sigma squared, I have to normalize. So I take xi minus mu divided by sigma, right? And when I say normalize, I meant standardize. Standardize means subtract the mean, divide by the standard deviation. So standardize. And then I do over square root of 2 pi. And then remember there's a sigma, because whenever you stretch, there's a sigma in the denominator. That's your density. Now I can write the density as, well, I'll let you do the algebra yourself. It's 1 over 2 pi to the power n over 2. Right? That's all those guys. There's also sigma to the power n. Then there's e to the minus 1/2. And because the product becomes a sum when you're doing the exponents, so product of e to the x's over e to the sum of the x's, so sum I equals 1 to n of xi minus mu squared divided by sigma squared. Okay, so that's what the joint density is. Now let's jump straight to the log likelihood, because obviously there's a lot of constants and paraphernalia that would make it harder to differentiate if I left it like that. So log likelihood of mu sigma given x is equal to, what's the log likelihood? Let's take logs, and okay, because I don't like to be dishonest, I'm just going to say omit constants. Okay? So an additive constant in the log likelihood would be everything to do with that. Sorry, the 2 pi to the n over 2 is an additive constant. Now sigma is considered a parameter, so that one doesn't get omitted. So that will come at the end. So it is minus 1/2. See, natural log just gives me the whole thing in the numerator, xi minus mu squared. Why don't I put the sigma minus 1 over 2 sigma squared? I might as well put that on the denominator here. And then I also have minus n natural log of sigma. So that is, after omitting the constants that don't matter, the likelihood. Now, here's a function of 2 variables. You'll have to think a little back to your calculus course when you wanted to think a function of 2 variables that's differentiable in both to find a maximum. Well, first of all, when you restrict to mu varying, it should be a maximum. And when you restrict to sigma varying, it should also be a maximum. And that tells you that the 2 partial derivatives should both be 0. You've got 2 inputs, you have to set both partial derivatives to be 0 and solve to find the maximum. And then the little criterion I did here is for it actually being a maximum gets a bit harder in 2 dimensions. You actually take the Hessian. Now, I'm not going to go into that because it's not a calculus course, but just so long as you're aware, if you're doing anything other than it, here you can just accept my word for it that it is actually a true maximum. But if you're not, you should do a bit more calculus to check that it's a true maximum, especially if there are multiple candidates. Function of 2 variables, set dl by dx, that's a partial derivative, and dl by x mu. dl by d mu and dl by d sigma both should be equal to 0, and solve to find the maximum. Okay, if it exists. So all the issues of existence and uniqueness, I'll just leave those out. I don't have a lot of time right now. So, but let's do partial L by U. Now, it's the same parameters, but I'm just not going to bother writing it by mu, not U. Partial L by mu. You see, all of these, remember, in the likelihood, x is a constant. That's the key thing. And if you're doing partial with respect to mu, then sigma is a constant. So that's minus 1 over 2 sigma squared. Sum I equals 1 to n of derivative of xi minus mu squared is 2xi minus mu with a minus sign because of the mu. So that's 2 mu minus xi. Okay? And then I have minus n log sigma. N is constant. And sigma, for the purpose of d by d mu, sigma is constant. So we just have to set that equal to 0. And we also have to set dl by d sigma to be equal to 0. And that, in this context, is equal to dl by d sigma. Okay, we're going to have 2 terms, but when you're doing d by d sigma, mu is considered constant. So that will become sigma to the power minus 2 gives you a factor of minus 2. So that will become 1 over sigma cubed, sum I equals 1 to n of xi minus mu squared, when you're differentiating that. And then the minus n log sigma will become minus n over sigma. Okay? So let's, if you're, by the way, we'll have a bit of cancellation for a 2 with a 2 here. So let's just solve these. We're actually going to get 2 equations in 2 unknowns, and we need to solve to find them. So, but luckily this equation, when I solve that, you see that because sigma is always positive, it doesn't actually matter that there's 1 over sigma squared times something equals 0. That's sigma is positive, so I can just get rid of the 1 over sigma squared. That means sum I equals 1 to n of mu minus xi equals 0. So clearly n mu equals sum of xi. So mu has to be equal to x bar. So straight from the first equation I solve and I find mu equals x bar. And then on the second equation, I know that mu equals x bar, so that means, let's multiply through by sigma to the power 3 so I don't have denominators. Sum I equals 1 to n, xi. Now I'm allowed to put mu equals x bar because that was the only possibility here. Xi minus x bar squared. So from the first equation I've got mu equals x bar. Minus n sigma squared equals 0. So, I mean, by the way, this is mu map. And then I would the conclusion is that sigma squared, okay, so this is the solution we're going to find, is equal to 1 over n. Notably, not the sample variance, I equals 1 to n of xi minus x bar squared. So the sample variance, of course, would be 1 over n minus 1. So to fix that up, I could write it n minus 1 over n times s squared. So interesting fact, the maximum likelihood estimator of sigma squared is not s squared. The reason we preferred s squared was that it is unbiased. There's no guarantee that either the method of moments or the method of maximum likelihood will give you something that's unbiased. And so this was effectively, if you think about how did people come up with s squared, well, it's related to the maximum likelihood and the moment estimates, but it's a slight fix because if we can, we would prefer an unbiased estimator. And by the way, that doesn't affect consistency. Of course, maximum likelihood estimator and moment estimator, this is still consistent for sigma squared. Because, and then s squared is still consistent because the issue of whether it's n minus 1 and n, in the limit as n tends to infinity, that factor is 1, so the consistency is unaffected. It's a fix for low values of n because you would prefer to be unbiased if you can. Okay, that's our first big example of maximum likelihood. Now, you can solve essentially all of them by this point. Okay, so I'll just say worried about is it a true max? Okay. Now I don't want to go through all the general mathematical considerations about is it a max of a thing, but let me just remark, and this will be very frequently true, not the likelihood itself. The likelihood itself is positive, and that tends to give a lower bound that's not exactly what you want. But the log likelihood is actually concave down. Is that what we call it? Concave down? Yeah. So, and that implies, at most, or it implies any place with derivative 0, dl by d mu equals dl by d sigma equals 0 is a maximum. That's a fact. Whenever, you can just think geometrically about it. If something is curving down in both directions, in all directions, and then you find something that's a point, that must be a maximum. Okay, so that's in case you're worried about that. So next time we'll do more examples of maximum likelihood. This might seem ridiculous for the last minute or two, but I just want to talk a little bit about hypothesis testing. And we'll do a lot of this in chapter 10. But let's just do a basic example. A basic example of hypothesis testing. The way you have a setup is H0, and let's say this is in the proportions. So this is the same proportions as earlier today. Okay? If you have a hypothesis about the true proportion versus the alternative hypothesis, let's say two-sided P not equal to P0, we'll set up the terms of this a whole lot more later. But if I want to test this, we know, and this is only going to be an approximate test, we know approximately that P hat has a normal distribution. We talked about this before, centered at P naught. It's divided by square root P hat 1 minus P hat divided by n. That's, now, how good an approximation that is, you might want to check the rule of thumb. I said of np at least 10, n1 minus p But approximately that is normal 0, 1. And we'll call that Z. And so we reject the null hypothesis at the alpha significance level. This alpha is the same as before, often 5% level, if absolute value of Z is greater than Z1 minus, we call this Z alpha.